All right, welcome. Um, Today is the first day we're actually going to do anything fun. I've had, I don't know, I've had trouble. It's like they set me up because what I did was I looked through, I just quickly, I didn't look at grades or anything because I was just trying to get an idea of what courses you've taken in the past. So just quickly, I flipped through your transcripts and just to get an idea of where you are kind of math wise. And from what I can tell, a lot of you don't have any calculus, and that's fine, except this course kind of assumes a little bit of calculus. So keeping that in mind, I'm going to try to keep it as very basic as I can, okay? And maybe you have a calculus course that isn't on your transcript at the college or something like that. That's great. But if you're like me, it's been a while since you took calculus anyways. So when you're reading chapter 1, right, there are mentions of integrals, and we will use them, but I'll very much show you exactly what to do. And I can't assume that you have any calculus background. I'm not sure why they would set me up to fail like that, but I'm going to prove them wrong. We're going to prove them wrong, right? Okay. So just as a quick reminder, you do have that markdown practice file or the markdown test file that you're going to submit. That's due tonight. I saw a lot of submissions already. I know chapter 1, it's like blah, 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 blah. I tried to boil it down as much as I could. So we'll see how it goes today. But it is good to read the chapter, right? Especially because I posted chapter 1 for you guys to read through. So try to read it, at least if you've seen it once. Now, we're not going to get very far at all today. I think we'll get about halfway through 1.2 today, but that's because I want us all to have a really solid foundation. So try to read it. Maybe it won't make sense. That's okay. Hopefully it'll make sense after today. Okay. The reminder. So I saw a lot of submissions already, so that's great. I didn't look at them, but I'm assuming they went well. So reminder, markdown test document is due tonight at, I always do 11:59, right? Because midnight is kind of confusing, but it's basically midnight. Okay. And so if you're having any troubles with that, let me know and we can meet after class today and we can get it all sorted out. But otherwise, that's due tonight. Okay. So typically what I do is I have kind of pre-typed notes and then I grab those and then I talk around them. But after reading chapter 1, I thought, oh, no, I don't want to have anything kind of pre-typed or anything like that. So we're going to write out these notes together. Of course, I do post these notes after class, right? So if you're the sit back and listen type, then that's totally fine. I will be posting the notes, but what I did was I did my chicken scratch notes on the side here. So I will be reading off of these notes because I'm feeling pretty good about these notes. And that's not really how I like to do it, but I'm trying to keep it as clean as I can. If you haven't had a look at chapter 1 yet, you'll know what I mean when you have a look at chapter 1. All right, so I already warned you that we're not going to get too far into chapter 1 today, but I do want to get a chunk of 1.2 done. So here we go. Chapter 1 is called Probability and Distributions. Side note, I found a lot of typos in the textbook. So that feels weird, right? And you probably have too, but I think in general, it's okay. There's a lot of long sentences though, unnecessarily long. What was my favorite? So what I did was I made this has been like a multi-step process. I read the chapter, I made summary notes for myself, and then I summarized my summary notes. Yikes. My least favorite sentence so far. Now conceive of our having made, instead of saying, pretend that we made n trials, right? Repeated performances of the random experiment. Terrible. That's such a long, useless sentence. Anyways, just wanted to point that out. Yeah, it's like they're trying to make it sound more complicated than it was. It's not that complicated. It's so weird. It is complicated, but they're like trying to make it complicated. So I'm trying to, yeah, are we in law school or what exactly? Yeah, so weird. So I've tried to unwrite it and just make it plain. Okay, hopefully you guys are okay with that. I know I would be. I am. Okay. So 1.1 is just an introduction. They did my least favorite thing, and I think they started with, we start with an intuitive introduction, but then they don't really explain it. Anyways, this is where I want to start. So we have to start by talking about, if we're moving towards probability, what happens is we need to establish, well, how do we have an idea of what a probability is, right? So that's what we're going to build towards in this introduction. But in general, oh, I just realized, how do I start that live transcript here? Enable. Okay. I think it started. I like that thing. I don't think I've never used it before this term, but I like it. And it's so quick. I love watching it type. Anyways, oh yeah, so what we're establishing here is just the idea of probability. Now, if I ask you, okay, if you flip a coin, and we know that there are two possible outcomes, right? When I flip a coin, it's either heads or tails. I know you can land on the side. We're going to assume that can't happen. Okay, so it's either heads or tails. So we have two possible outcomes. What if I just asked you, what's the probability of heads, right? Assuming that you have an unbiased coin, right? So it's just a normal coin. And we have an idea of, okay, well, it should probably be a 50-50 split because I have two possible outcomes exactly. So 1/2 probability of 0.5 is what our brains have been trained to do. But that 0.5 comes from something a little bit more complicated. It comes from, okay, if we assume that we can flip a coin, in theory, an infinite number of times, right? Or a very, very large number of times, then the number of times that we get heads, for example, is going to stabilize, right, around 50% of the time, or 0.5, right? And so that's what we're developing here, and that's the idea of probability, right? So we're starting with probability, and from stat 230, depending on kind of who you had, you probably have done some probability before, and so this would just be review, but here we go. So an investigator, that's us, right? An investigator performs an experiment, It's not necessarily an experiment, but for the purpose of developing the idea of probability, we're going to call it an experiment. But if you prefer, we can call it or a study. Okay, so, but we'll call it an experiment to gather information. That's in general, right? Some of the examples that they give in the textbook are, maybe we're interested in the effect of a drug, right? So maybe we have a clinical trial and we're interested in the effect of the drug, right? Maybe we're interested in the prices of 3 specified commodities at various time intervals, right? Maybe that's the price of gas and lumber and I don't know, I can't think of anything else. Copper, maybe, right? So at various time intervals, right? Quarterly, yearly, whatever. So the prices of 3 specified commodities at various time intervals. Or maybe we're interested in the effect of a chemical fertilizer on the yield of a cereal grain, stealing it right from the textbook. But they've got all the good, they've had time to sit down and think of some good examples, so I'm going to use them. Right. The effect of chemical fertilizer on the yields of a cereal grain, right? If you're a farmer and you're growing some sort of grain, right? Oats, wheat, whatever, then you might be interested in studying the chemical fertilizer and its effect on the yields, right? Regardless of the experiment, right? The experiment is going to end in some outcome, right? So each experiment terminates in an outcome. So usually we're interested in that outcome, or later a set of outcomes. Okay. So once you do an experiment, right, you get some sort of outcome, and it's that probability that we're interested in. Okay. So, however, the outcome, right, we don't know the outcome until we've done the experiment, right? And so, however, the outcome cannot be predicted with certainty prior to the experiment. Okay. So what we're going to say is that if we can identify all the possible outcomes, right, even though we don't know exactly what's going to happen, right, if we can identify all the possible outcomes of an experiment and we can recreate that experiment with the same conditions, then we have what we call a random experiment, right? And so if the collection of every possible outcome of an experiment can be described prior to the experiment and the experiment can be repeated, and the experiment can be repeated under the same conditions we call it a random experiment. So a lot of definitions here, right? But this is just so that we're able to have that terminology later when we're reading questions, right? Because all these, we have to be really careful when we read questions. Okay. This one might be familiar or should be familiar. The sample space, right, so the sample space is the collection of all possible outcomes, right? And just as a heads up, I do have a page break here, so it's going to look like I'm cramping it together, but that's because I know it's going to get split up later. So don't worry. I know it looks weird, but it's okay. The sample space is the collection of every possible outcome. Wait, hey, what happened there? I don't know. It must have hit something. Of every possible outcome. In kind of light blue here, I'm going to say that it's denoted by, it's kind of like a fancy capital C, but it's probably going to end up looking more like just a normal C. So maybe I should just do a capital C like that. Okay. Now, I know at least when I teach kind of intro stats or elementary stats, so stat 230, I definitely use a capital S, right? So, or a capital S for the sample space. That's just what I prefer. But this textbook is going to use capital C, and we need to be kind of okay with new notation. And because they've probably used S for something else. So I want us to be okay with just using a capital C and just say, yep, okay, got it. Right. And so my master's supervisor, he would do things like he would tell us a bunch of facts at the beginning of class, and then he would do little quizzes throughout. So things like he would say the sky is red, 4 + 2 is 7. And then we would have to just say, yep, okay, yep, that's a fact. And then we would have to use that, right? And so I want you to kind of get into that groove where, okay, C is the sample space now. All right, moving on. It's not that bad. I'll highlight the sample space here because we're going to be using that term a lot. Okay. Quick example, we actually already talked about it, right? But in terms of the sample space, if a coin is tossed, there are 2 possible outcomes, right? There are 2 possible outcomes. Right? Heads or tails. Now, I'm using capital letters here to denote these outcomes, right? Heads or tails, depending on the context, right? Sometimes it'll be obvious. Sometimes we'll have more general notation, but especially when it's so obvious that we're tossing a coin, okay, and we know those 2 outcomes, usually we'll use kind of an abbreviation like this. Okay. So how we denote the sample space then is using a set, right? It's a set of outcomes. And so C in this case, C equals the set of H or T, right? And so here, this is, maybe I should use a different color. A set of H and T. Okay. So we've got these curly brackets to indicate that this is a set. And so the list of all possible outcomes is either heads or tails, right? And that's all that can happen. It's one of those is going to happen, right, in one flip. A little bit more advanced, right, is if we incorporate, maybe I'm tossing a die, right? So we assume that we're only talking about a 6-sided die, right? So there's one side with 1 and then one side with 2, 3, 4, 5, 6, right? And so we assume that we just have a basic die. And so that makes it a little bit more complicated. You can do things like, what if I flip a coin and roll a die, right? And the combination of the possible outcomes, right? Or what if I have 2 dice, right? And a student of mine a long time ago told me that, oh, because I had such a hard time with die or dice. And he said, well, you can only die once. So that's why it's singular is die and then 2 dice, if that helps. So the other example is if we cast 1 red die and 1 white die, I find it really helpful. At first I was like, oh, that's such a weird, no, it makes sense. Okay. So if we cast 1 red die, now the color doesn't actually matter, but it's to help us remember that, okay, there's a red one and a white one. Totally, right? It is weird, but it makes sense. So here we've got the color just to help us kind of see the differences, right? But we don't need different colors. We might just be rolling 2 dice, right? So what we're going to do is we're going to say, okay, I've got a red die and a white die, and I'm going to roll them at the same time. And then I'm going to record the number of dots that are facing up, right? And I'm going to record them as if they're ordered pairs. Now, remember, ordered pairs are things like X comma Y, right? On a plot, that would be an ordered pair. So we can do the same thing. I'm going to remove this here. We can do the same thing. We just need to decide the order that we're going to list them, and then we stick with that order. And 1 white die and record the outcome as an ordered pair. Like this, where we have a round bracket to indicate that this is an ordered pair, the value of the red, comma, the value of the white die. Okay. So the fact that these have different colors help us realize that, okay, well, the number on the first die, right, is separate from the number on the second die, right? But because they're different colors, it's easier to see that a 1 and a 2 is different from a 2 and a 1, right? The result is the same, right? But it's easier when we have these 2 colors to see that, okay, well, a red 1 and a white 2 is different from a red 2 and a white 1, right? And so the ordered pairs, now order matters, right? So what if we have to list all the possible outcomes, right? And so, oops. We can list the possible outcomes. And it takes some practice, right? But there are some go-to possible outcomes that we use, right? So rolling 2 die is pretty common. So we can list the possible outcomes. And if we're just starting, right, then we could have it set up like a table, right? Where we can have, now how does it have to be? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Right, and so I guess I'll use black for the white die. That's weird, right? But here's the white die, and then I have red, so I'll use red here. Okay. So the possible outcomes, right? If we're listing these ordered pairs as the value of the red first, and then the value of the white, right? As we move across here, the first value in the top row is going to be 1. So it can be 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. Then we move on to the second row, right? Now I can have a 2 first, and then a 1, a 2, and a 2, 2, 3, 2, 4, 2, 5, 2, 6, right? And so let's see if I can keep my wits about me here. 1, how about I do this? 1, 1, 1, 1, 1. what am I doing? I'm just setting up these blank combinations, these blank ordered pairs. So now I have 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, right? And we keep doing that throughout. So we'd fill in all these ordered pairs. How many possible outcomes are there? 6 by 6, right? So 36 possible outcomes. So here we see there are 36 possible outcomes. Yeah. Does this cover all the possible scenarios? Yes, it does, right? Because here they all take a turn. All the possible outcomes take a turn at being first, and all the possible outcomes take a turn at being last, right? And so we'd fill all this in, or what we can do is we can use ellipses and we can just list them like this. So we can say that C is the set, and we can use set notation for ordered pairs as well, right? But we need to make sure that we're fully explaining the entire set, right? And so we might do that by saying it's the set of 1, 1 up to 1, 6, followed by 2, 1, all the way up to 2, 6. And then the reader should have an idea, and it goes all the way to 6, 6. Confession time. Usually my left curly bracket looks okay, and then my right curly bracket, you never know what's going to happen over here. It's harder, right? They'll never look the same. That's guaranteed. All right. So we have our sample spaces, and that's going to be really important, right? Yeah, it's a snake. Snake eyes. I'll make them green with black dots. It's a snake with an eye. Yeah. So, so listing all the possible outcomes is definitely going to help us figure out probabilities, right? Because if we know how many possible outcomes, just like when we flipped a coin, right, knowing that there are 2 possible outcomes, it gives us some idea of the probability of one of those outcomes happening, right? 50-50 likely. Right. So here, knowing that there are a total of 36 possible outcomes, right, that helps us in the sense that, okay, well, then each combination, right, assuming that it's not a weighted die, these are fair die, right, then each possible combination has a probability of probably 1 over 36, right? They each have the same probability. And so that's kind of what we're building towards here. Okay. So some more notation, I'll put on this fresh page here. We generally use lowercase letters to denote elements. Now, so each of these things, right, each of these possible outcomes is called an element. Okay. So we generally use lowercase, and I will throw in Roman letters for elements, right? So things like A, B, C. right? So lowercase, just normal letters, A, B, C. We typically start at the beginning of the alphabet, but then there are cases where, okay, it makes sense to talk about T and H if we're flipping a coin, for example. So then we stray, but typically, just in general, we use lowercase letters. We're not usually concerned with just a single element, right? We're usually talking about a collection of elements, right? What's the probability of the sum of these being 2, for example, right? Well, there's only one outcome where that happens, right? But what if we talk about the sum of these being 6? Right, there are a couple of ways that we can get a sum of 6. We can add 1 and 5, or 5 and 1, right? 2 and 4, 4 and 2, 3 and 3 is the same as 3 and 3. But we're often concerned with the chances, and chance is later going to evolve to probability, right? But for now, we're going to stick with the word chance because we haven't established it yet. But we're often concerned with the chances of certain events happening. Okay, so an event is a subset of the sample space, right? And so it's usually a group of elements. Usually a group of elements. Okay, so we've got elements and events. Can't remember if I highlighted element earlier. Random experiment. No, I talked about outcomes. How about I'll highlight it there. I didn't really define it ever, right? But it's one thing or one outcome. But we're quickly going to move to a group of elements, which is an event. Okay. I'll have to make a note to add that in later, but it's okay. So we're talking about events, right? So which is going to be a group of elements. So like the example that we just did, right? If we're talking about the sum of 6, right? Where the 2 die add to 6, there are a number of possible elements here, right? So now we have a collection of elements, and that's going to make the event of adding to 6, right? What gets tricky with this terminology is that sometimes element and event are used interchangeably, because there are cases where an event is just one element, right? So it's a group of one thing, and then it's just an element. So it can get a little bit sticky, right? But typically we can use event and elements interchangeably, depending on the situation. So usually an event is denoted by capital letters. And again, we typically start at the beginning of the alphabet, A, B, C, etc. C in this case is reserved for the sample space, right? But it is an event. It's all the possible things happening, right? And so it still stands. So if an experiment results in an element of an event A, okay, then we say that A occurred, right? So only one of the things can happen, right? And so if something in the event A happened, then you say that the event A happened. Okay? So if an experiment results in an element of an event A, we say the event A has occurred. And so what we're going to end up thinking about is, okay, so now we want to know the chance of A occurring. We are interested in the chance of A occurring. Okay. So for example, right, if we think about the chance of the set A is just heads occurring. Oh. Occurring is so hard to spell. OCCURRING. Right? So it's out of context, but it should be obvious what we're doing here, right? We're flipping a coin once and it's either heads or tail. And now I'm defining the event A as a heads happening, right? With two possible outcomes. We guess that the chance is 1/2 or 0.5, right? Which we already talked about. What if we want to talk about kind of a broader event, right? Something a little bit bigger than just tossing a heads, right? So for example, what if we want to talk about the chance of the sum of two dice being 7 or 11? Okay, so I want you to pay attention to that or. Okay. So what are some of the ways that we can get 7, right? A sum of 7. We can list our event. A is, well, it can be a 1 and a 6. It can be, right, focusing on the sum of 7 first, right? 1 and 6 or 2 and 5, or maybe 3 and 4. I think in terms of a regular die, those are my only options, right? But now I want to do them in reverse, right? Because I could also have a 4 and a 3 first, or a 4, then a 3, or I could have a 5, then a 2, or I could have a 6, then a 1. And notice that these are all unique events, right? Or unique elements. Okay. So now I feel pretty good about having all the possible ways I could get a sum of 7 under control here. And you could confirm it, right? You could confirm it by looking at this graph here by just figuring out the sum of each of these. But I'm feeling pretty good, right? So what are some of the ways that we could get a sum of 11, right? Well, 11, I'd have to go for just 5 and 6, right? These numbers aren't large enough, so those are the only two that are going to give me a sum of 11. So it can be 5 and 6 or 6 and 5, right? So I'm going to list those here. So I could get 5, then a 6, or a 6 and then a 5. Sum of 7 versus the sum of 11, right? So notice when we have this or here, it can satisfy either of those criteria. Okay. So I've got 1, 2, 3, 4, 5, 6, 7, 8 elements in this event. 8 elements in A. Okay. Now, knowing that I have a total of 36 possible outcomes, then I'm feeling pretty good about saying that the chance of A happening, right? So the chance of a sum of 2 dice being 7 or 11 is going to be 8 over 36. But I'm going to hold off on that for just a tiny bit longer. Okay. Until about now. So again, I've got a page break, so I'm going to smush them together, but say we repeat an experiment capital N times. Okay. So if we repeat an experiment, and the easiest way to think about it is if we're flipping a coin N times, right? So maybe 10 times, maybe 20 times, then I can record how many times I get tails, for example, right? And so how I would record that is using F, a lowercase f, to denote the frequency that I get tails. Okay? And so we could count the number of times N, sorry, not N, the number of times A occurred. Yeah. We denote this denoted by a lowercase f for frequency, right? The frequency of the times that A occurred. Okay. What we're going to use this frequency for, or this theoretical frequency, is for the relative frequency, and that's where a star is born, right? That's where probability is born. So the relative frequency is F over N. And I should maybe make it look a little bit nicer. lowercase f over a capital N. Okay. What happens if we're looking at a small number of trials, right? So a small n, then the relative frequency is going to be quite erratic. Okay. Whereas if we're looking at large samples of n, so large number of trials, then what we're going to find is that frequency, that relative frequency is going to even out. And then we end up at the probability. So the relative frequency is f over n. So for small values of n, the relative frequency is quite erratic. But as n increases, the relative frequency stabilizes. And I guess I should finish that sentence with, and we call this value a lowercase p for probability. And we call this value p. And just a lowercase p. So p, okay, is the probability that the outcome of the random experiment is in A. Remember, it doesn't have to be all of A, it just has to be somewhere in A, the event. So P is called the probability that the outcome, the outcome of the random experiment is in A. Okay. Sometimes it's just called the probability of A, or even the probability measure of A. For us, I'm probably just going to call it the probability of A, right? So sometimes, or most often in my case, sometimes it is just called the probability of A. Right? Rather than the probability that the outcome of the random experiment is in A, right? We can just say the probability of A happening, right, or occurring. Or the probability measure of A. So in terms of a quick example, right? Let's see here. If we let's C, so the sample space, let C be the sample space from that red dye and a white dye, right? So let C be the sample space from one red dye, or one red and one white, just to keep it A little bit quicker. Then what we're going to do is we're going to let the event B, notice I'm using a different letter here, B, be the collection or the set later, collection of ordered pairs that sum to 7. Okay. So if we have to list the event B, right, all the possible outcomes in B, well, we know it's 1, 6, 2, 5. We already did these, right? 3, 4, 4, 3, 5, 2. Key is to just work backwards. 6, 1. And we're only interested in a sum of 7 in this case. So hypothetically, let's say we roll these dice 400 times, right? So we let n be 400. And then we find that the outcome that we get is in B 60 of those 400 times, right? And so we're going to find the relative frequency. So if we cast the die, n equals 400 times, and find the frequency is 60, right? The relative frequency is the relative frequency So in this course, we're going to work on firming up some just kind of how do we write math properly, right? And so what I want you to do is I want you to start with the empty formula that you're filling in. And I skip it sometimes, and that's bad. I'm going to try not to, but we should show that the relative frequency is F over N. And then what I want you to do next is I want you to stack your equal signs, right? And so if I'm running out of page or kind of room on a page, then maybe I'll go across sometimes, but it's bad, right? We should try to stack our equal signs as much as we can. So in this case, when I fill it in, right, I get 60 over 400, which is 0.15, right? So P is 0.15, is the probability of the event B. Good. All right. Shame I just started a fresh page. Oh well. 1.2 is on sets. So that was just like an introduction. It was long. It was kind of, where are we going? Probability. That's where we're headed. Okay. So now we're going to talk about sets. So sets, you've probably worked with sets at some point, probably set 230, right? But I know some teachers who teach it like to go really heavy on it and some don't. So I don't know where we stand, but here's a good review. Okay. Or at least a reasonable review. So a set is a collection of objects in general, right? Or a collection of elements. The key thing about a set is that we should be able to describe the set so fully that there can be no misunderstanding of what's going to be in the set and what's outside of the set, right? And so that's going to be important. And so let's write that down. We should be able to describe a set so there is no misunderstanding as to what collection of objects is under consideration. As to what collection of objects is under consideration. Okay. There are two really common sets that we're going to use, and it's kind of assumed that you know. And so some common sets, oops. First, we have the set of integers. Okay, the set of integers is denoted by a fancy Z, right? A fancy Z with a back. Okay. And what is the set of integers? Well, it's the set of whole numbers from negative infinity to positive infinity. Okay, and so how we denote this set is, dot, 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 up to, I'll pick up at -3. You can decide -2, -1. It includes 0, and then not -1, 2, 3, dot, 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 end of the set, right? And then the dot, dot, dot indicates that it's going to infinity in either direction, right? One thing that I've noticed in this textbook is that they like to define the set as the set of positive integers. Okay, so the set of positive integers would be here, right? So it is assumed that you know that, right? So the set of positive integers is going to be 1, 2, 3, 4, 5, 6, 7, 8, blah, 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 all the way to infinity. Okay. What's another really common set that we're going to use? Well, it's the set of real numbers, which is also kind of a fancy one. It's an R with a back, right? The set of real numbers. And it is just going to be from negative infinity up to positive infinity. So it's everything on that continuous number line. So it's basically every number, well, not basically, it is every number that exists. So every real number that exists. And so any number from negative infinity up to positive infinity is in the set of real numbers. Okay. So just as an example, to practice reading these a little bit, what if we say the set of the first 10 positive integers, there it is. Okay. So think about the set of the first 10 positive integers, right? And so that's going to start here at 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And so that's the set that we're talking about. Okay. And so we could ask something like, is 3 in the set? Well, it was on the list, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, it's in the set. Is 14 in the set? No, because it wasn't on the list, right? Is 3/4 in the set? No, right? Because it wasn't on the list, right? And so we know 3 is in the set, while 14 or 3/4 are not in the set, right? So the key is to define your set so that it's obvious if values are in there or not. Okay. If an object belongs to a set, it's called an element of that set. So if an object belongs to a set, it is called an element of that set. That's the element that I want you to remember. For example, if A is an element of the set A, context can be really important here. If lowercase a is an element of the set capital A, right, then we write that A is an element of A. So we use this kind of, I'll make it big here for a second. It's just a C with a line, making it look kind of like an E, right? So we've got this kind of C with a line, and that means is an element of, right? So lowercase a is an element of capital A. Is an element of, look at how much writing that saved us, right? Good. We might even write our sets a little bit fancier now. I'm assuming some set notation, that you've seen some set notation, but I'm not going to go too deep into it. The textbook goes into ordered pairs, but we'll do that if we need it later. So I'll just show you one other set. So we might write something like this, right? C is the set of X. Now the textbook uses a colon, right? But I kind of not grew up, but you know, through my undergrad, through grad school, we used a vertical bar. So if you've seen that before, right, we read it as such that, okay. So we're saying that C is the set of X's such that, and then we give the criteria for the X here. So in this case, let's say X is somewhere between 0 and 1 inclusive. Okay. So we might write this, and if we wanted to use kind of a longer description of what this says, right, besides saying that C is the set of X's such that X is between 0 and 1 inclusive, right, we could talk about, well, X is a one-dimensional set of points, right? So we could say to describe But as long as you know how to read it as C is the set of X's such that X is between 0 and 1 inclusive, I'm happy with that. But technically, we are describing the set C as the one-dimensional, only because later they discuss the two-dimensional set of points, but we'll just talk about the one-dimensional set of points. Set of points X, for which X is, and I'll clean up my X. I like to have my X with a little bit of a flare, because then I can keep track between 0 and 1. So we might use something like that for our set notation. So in this case, right, thinking about 3/4, right, 0.75, 0.75 is between 0 and 1. So 3/4 or 0.75 is in the set C in this case, right? In fact, all elements between 0 and 1 are in the set C, whereas 3 is not in the set C in this case, right? Just the definition, C is countable, and it's a little bit hard to wrap your head around, right? But it's countable if it has a finite number of elements. And what's the other part that I always, so it has a finite number of elements, but also has as many elements as there are positive integers. Remember, positive integers go from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way to infinity. Technically, in theory, you could keep going until you reach infinity. Infinity is not a number; it's a kind of a state of mind, I guess. And so, but in theory, you could go to infinity. And so they're saying that C is countable. I'll highlight that. If C is finite, meaning that we have a finite number of elements and has as many elements as there are positive integers. Okay. I'll list C1, C2, and C3, and we're going to identify whether they're countable or not. And to me, it feels a little bit weird with the second one especially, but here we go. So the first one is the set from 1 to all the way up to 100. It's finite, and it has less than the number of elements that have as the positive integers. So this is countable. What if we had something like all odd numbers, 1, 3, 5, 7, and we just let it keep going to infinity? This is where I have a hard time wrapping my head around it, because in my mind, it's not finite, but how they're thinking about finite is that you could keep going and going and going. There's nothing stopping you, right? But you'll never really reach the end. So to me, that's the hard part. But the key is that and has as many elements as there are positive integers. And so there are fewer elements here than there are positive integers. And so as many, I think it should say as many or fewer, but I'll correct that and get back to you next day. But I'll look that up. But this is countable. Versus if we have the interval from 0 to 1, not including 0, but including 1, right? Then we have an infinite number of values in here, and we could never get a handle on how many we have. And because it's on this continuous scale, right, it's not countable. Okay. Wait, when do we end? Is it now? Oh my gosh. Well, not, yeah, now sort of. I'm gonna have to check my phone to see when we're supposed to end. Oh my gosh. It's now. Okay. All right. So that's a pretty good place to stop for today, I guess. We'll start talking about just kind of some set facts next day. How about? All right. If you have any questions, let me know. Otherwise, I'll see you on Thursday. And I'll stop this recording here.